So what we're going to work on here is inclined planes. We're also going to want to just drive home the point of what we do when we have any problem where there's forces at an angle, and how we go from the free body diagram, which will show the forces at an angle, to a component diagram, which just gives us things that are either horizontal or vertical, breaks all the ones at an angle into their components. So for this, let's start with the uniqueness of the inclined plane, the ramp, whatever you want to call it. You generally call it an inclined plane. And as a quick preview, the angle that they give us here is going to end up not being a reference angle, and so there's going to be a little bit of a trick with that down the line. But before we get, not a trick, but a little way to handle, a couple ways to handle that. Now, the other thing we have here is that if we use a regular coordinate system, in other words, a coordinate system where, say, this is my y-axis and this is my x, it will turn out that my acceleration will be, let's see, in this case, if there is an acceleration, parallel stress. All right, so for example, this acceleration that they're talking about is actually going to be, would be this direction along the upward part of the ramp, because that's the direction it's moving, that's the direction, in this case, the acceleration is pointed. And that means our acceleration would have components, would have to be at an angle. And that's going to make this problem so much harder. But there's a way around that. So if we have an inclined plane, the first thing to keep in mind, or the first thing you want to do, is this. The coordinate system that you see here is, there's no law that says it has to be vertical and horizontal. In other words, no law that says that the x has to be horizontal and the y has to be vertical. The only, quote, law there is they have to be perpendicular to each other. So what we can do here is take our axis, for example, our y-axis, and our x-axis, keep them perpendicular, close to it in this case, let's see, there we go, a little better, there we go. Keep them perpendicular to each other, but tilt them like you see here. So what we'll have is a situation where the acceleration and the net force will be back and forth on the x-axis and not at an angle to anything. So you just tilt your head and you look at the problem where the surface of the inclined plane is the x and anything perpendicular to it is the y. And it's going to make this problem a lot easier to handle. Because what it's going to do is it's going to take not only make our acceleration and our net force either left or right, in this case I think to the right, it's also going to make normal force along an axis. For example, the normal force would be right here. Normal force is always perpendicular to the surface, and in this case, the surface of the plane. The tension in this case, created by that pulling, that's going to point this way as well. Friction is going to oppose that, and I believe there is friction, yep. And that's going to go this way, because the log, they tell us, is moving up the ramp. So force of kinetic friction if it's moving. The only strange part about this is right here, is that weight still acts straight down. It does not care that you turned your axes. The weight of the log is still straight down. And so we have a situation where the weight is actually, strangely enough, in the third quadrant, and will have components. I will sketch those on here in green, but we wouldn't normally put them on this diagram. But the weight would have a y component, mgy, and an x component, in here somewhere, mgx. So how do we find those components? Let's take a moment and make an honest to goodness free body diagram, not one that's drawn on top of the drawing, and do a component diagram as well. And when we get to the component diagram, we will discuss what we do with the x and y components of the weight. So I tilt my head back from where it was. Remember, I got the y-axis here, I got the x-axis here. We said tension was going to be this way. We said normal force was this way, along that. And we have friction going to the left. Oh, we have two forces ultimately going to the left. We got friction. And then friction, kinetic friction. And we have that weight sticking down in here into the third quadrant, mg. And there's our free body diagram. But that weight at the angle we need to deal with that, because we need to get that into components if we're going to be able to work with it. So we need to get this into its y component and its x component. Now, we know that generally we find x using cosine and y using sine. My suggestion for this, however, is that rule assumes that you're using a reference angle at least. And this angle, as I mentioned earlier, is not a reference angle. It is actually this angle, the complement to the reference angle. It's the one to the y-axis. And the quickest way I can tell you to get and take care of that is this. Is that for an inclined plane, it turns out, well, for any time you want to use the complement of the reference angle, it turns out like this. In fact, let's just do this real quickly, just to show you. So I'm going to make up an angle. Let's say I have an angle of, what angle do they give us? Maybe we'll use that. 34.6. Let's use a simpler number. So let's say I've got an angle of 30 degrees. Let's go 35 degrees. So 35 degree angle. Let's consider its cosine. So I hit cosine, boom, I get that number. I'm just going to jot that down. It's 0.819. Just remember that, 0.819. Now, what is the complement to a 35 degree angle? In other words, what do I have to add to 35 to get 90? And it's going to be 55, right? Yes, 55. So watch this. If I do 55 degree angle, but I do its sine instead, I get the same number. So in that little example, the cosine of a 35 degree angle is equal to the sine of a 55 degree angle. This will always be true, that for example, the sine of a 20 degree angle will equal the cosine of a 70 degree angle. So what we're going to do is since we don't, this angle here that they're going to give us, and they almost always give you that problem in an inclined plane, that angle in an inclined plane, we're just going to, for inclined planes, we're going to remember, hey, let's switch the sine and cosine when we're finding the components of the weight. So, for example, I'll go down here, and we're going to work on those components now. So I'm going to take this. We're going to make a component diagram. I believe I've mentioned these in class before, but if I haven't, this is a component diagram. And by that, I mean a diagram where we take any forces that are at an angle and we break them up into their components. Of course, any force that isn't at an angle is going to remain right where it was. So, for example, normal force is going to stay the same. The tension is going to remain the same. Friction is going to remain the same. I'm going to shorten it a little bit because I need to, I think. And in fact, I'm going to even take a moment because I know tension is going to accelerate it up the ramp from what they say. So I'm going to anticipate that tension is going to have to be big to do that. Okay. And now I'm going to take this force, the weight, and get its y component and its x component. We'll start with the x. So the x component of weight is going to look like roughly this. And I'm going to call it mgx, which is going to be found, by the way, doing the weight, mg. Now, this is where the inclined plane switcheroo comes in. So we're not going to use, normally we'd use cosine for the x, but in this case we're going to use the sine of that angle they give us. Meanwhile, down here is going to be mg y component, the y component of the weight, which is going to be mg and cosine of the angle. So we switch the sine and cosine. So I have a component diagram here, and that is what I really need to make my various expressions and to solve the problem. So we're going to use that component diagram, now that we've got it, to work in, let's see, the excitement here is all in the horizontal dimension. We know that in the vertical, quote unquote vertical, right, the y dimension, which isn't quite vertical the way we look at it here, but we know in this dimension here that there's nothing interesting happening. That the normal force is the same as the y component of the weight. Not equal to all the weight, just the y component. So those two have got to be equal because there's no acceleration occurring this way. And all the acceleration is back and forth here. In fact, it's going this way, accelerating that way. So a quick statement about the y dimension. In the vertical dimension, or what I'll call the y dimension, gotta be careful, we know that normal force is equal to mg cosine theta. Same magnitude as the weight. What we're interested in really is the x dimension. And by the way, since friction's involved, this is going to be important down the line. But for now, in the x dimension, looking at our component diagram, assuming that this way is positive, that means I start with the positives, that's tension. So I got, well, Newton's second law first. Net force is equal to ma. But net force is also equal to, looking at my diagram, I got tension pulling to the positive side, tension. And I have two forces that are negative going to the left. I have the force of kinetic friction, and notice also negative, mgx component. Okay, so ma, the mass of the log times its acceleration, will equal tension. All right, let's take a second. Instead of writing force of kinetic friction, I'm going to take it to its next step, which is friction is mu times normal force. U kinetic in this case times normal force. Minus, all right, mgx, I'm going to write mg inclined plane, so sine theta. So I just took these two right here and filled them out a little bit. But there's still more we can do along those lines, because ma equals tension. Now, mu kinetic, but what is the normal force? Remember I said it was going to be important? Well, now's the time. Replace normal force with what it's equal to, which is mg cosine theta minus mg sine theta. Okay. Now I go back and we're going to see if we can figure out what are, now that I have, but notice, by the way, maybe this isn't a great way to do this, I didn't even look to see what the problem was asking me for. In other words, I analyzed the forces and went through this process, got to this point, and now I'm like, I wonder what they want me to solve for. So let's take a look and see what they're talking about here. So they want the tension. So they're looking for the tension in the rope given all this stuff. They give us the mass of the log, thank you very much, the angle, the coefficient of kinetic friction, the acceleration even. So we got a bunch of stuff. In fact, one of the things I like to do is when I have this expression like I have down here, I like to check off what I have and what I don't have. I know the mass, know the mass, know the mass. I can't divide it out because it doesn't appear here in the tension term. They give me the acceleration. They give me mu. They give me the angle. Of course, no g. All right, so the only thing I don't know here is, in fact, tension. So that's what I need to solve for. Okay. Now that I've got this set up, it should be fairly straightforward. We're going to add this and this to both sides, which is going to leave us with ma plus mu kinetic mg cosine theta plus mg sine theta equals the tension. Or, since I like having the unknown on the left, tension is equal to ma plus mu kinetic times mg cosine theta, the normal force, plus mg sine theta. And now I can plug in everything I have and see if I can use my calculator correctly and get the correct answer. So I'm going to try to do this. Remember, 205 is kilograms. All the way back up here, 0.692. That's an acceleration of 0.692, which is in the positive direction because we made up the ramp positive, so we're good there. Meters per second squared. Plus 0.846, I think it was. 864. Mu, which is 0.864, no units, times 205 kilograms, times 9.8 meters per second squared, times the cosine of 30 something. 34.6. Plus M, 205 kilograms, times G, 9.8 meters per second squared, times the sine of 34.6. So I'll push the buttons. I'm going to pause this recording because who wants to just wait while I push buttons? I'll push the buttons and I'll come back in a split second and let you know if I got the right answer. You should probably check to see if you can do it too. Make sure your calculator's in degrees. So taking this in stages, I have 141.86 newtons plus 1428.8 newtons plus 1140.8 newtons. And then adding those together, unless I made a mistake, I get a tension of 2,711 newtons. You can do a 0.5, I guess, if you want. And that's going to be up the ramp, positive, the way we set it up. Let's see if we're even remotely correct. Oh, I didn't print the answers here. Hold on. I got them in front of me. So the paper you probably have at this point has the answers on it. And yes, I can still do physics. So that would be the tension in this thing. So we've learned a couple things just to recap. What did we learn? A couple things to worry about with an inclined plane. Tilt your axes. Remember that switch the sine and cosine when you go to use this angle. It's probably the easiest way to handle it. And in general, anytime you have forces at an angle, write your free body diagram and then make a component diagram where you break everything up into its components. And it's the component diagram that you're going to use to set up your expressions and so forth. We'll try it again with there's another problem somewhere out there involving friction and a wall, and we'll look at this component diagram thing as well.